Quantum chips are not about to end the AI data center race. That framing gets the basic physics backwards. Quantum computers and the GPU-packed data centers powering today's AI boom are built to solve fundamentally different kinds of problems. And nothing coming out of any quantum lab right now is positioned to replace the other. That needs to be said plainly, because headlines pitting quantum computing against AI infrastructure as if one is about to make the other obsolete misunderstand what each technology actually does. What's real and genuinely significant on its own terms is this. In February 2025, Microsoft unveiled a quantum processor called Majorana-1, built on an entirely new approach to quantum computing the company has been chasing for nearly 2 decades. It's a real chip based on real physics that Microsoft says could eventually lead to far more stable, far more scalable quantum computers than anything built so far. It's also, right now, at the center of a genuine, ongoing scientific dispute, with some physicists openly questioning whether Microsoft has actually achieved what it claims. That tension, the promise, and the pushback happening at the same time is the real story here, and it's a far more interesting one than any fake end of the data center narrative. Let's start with what a quantum computer actually is, and why building one has been so difficult for so long. Every computer you've ever used, from your phone to the largest AI supercomputer, stores information as bits, each one either a 0 or a 1. Quantum computers use something different, qubits, which can exist in a mix of 0 and 1 at the same time, a property called superposition, and can also become linked together in ways classical bits can't, called entanglement. In theory, this lets a quantum computer explore many possible solutions to certain kinds of problems simultaneously, instead of checking them one at a time the way a classical computer does. For the right kinds of problems, mostly involving simulating quantum systems directly, like the behavior of molecules, materials, or certain optimization problems with enormous numbers of variables, this could offer genuine, dramatic speed-ups over classical computing. The catch, and it's a massive one, is that qubits are extraordinarily fragile. The same delicate quantum states that make them powerful also make them almost unbelievably sensitive to their environment. A stray vibration, a tiny fluctuation in temperature, even faint electromagnetic interference can cause a qubit to lose its quantum information entirely, a problem called decoherence. Most companies building quantum computers today, including IBM and Google, use qubit designs called transmons, or trapped ion systems like the ones IonQ and Quantinuum use, and they manage this fragility mainly through brute force error correction, combining hundreds, sometimes thousands of noisy physical qubits together to produce a single, more reliable, logical qubit. It works, but it means scaling up to a genuinely useful quantum computer requires an enormous number of physical qubits just to get a modest number of dependable ones. Microsoft chose a different, much harder path almost 20 years ago. Instead of fighting decoherence with brute force error correction, the company set out to build qubits that are inherently more stable at the hardware level, so they'd need less error correction in the first place. The approach relies on an exotic particle first theorized back in 1937 by physicist Ettore Majorana, called a Majorana zero mode, or informally, a Majorana particle. Here's the basic idea, in plain terms. Microsoft's device is built from ultra-thin superconducting wires, made of indium arsenide, cooled to temperatures near absolute zero. Under the right conditions, electrons inside these wires can pair up in a way that allows an extra, unpaired electron to effectively split its identity in two, forming a Majorana mode at each end of the wire. Instead of storing information in a single localized particle, the information gets stored non-locally, spread out across the wire itself, encoded in whether the wire holds an even or odd number of electrons overall. Because that information isn't sitting in any one physical spot, small local disturbances, the kind that normally wreck other qubit designs, shouldn't be able to easily disturb it. Scientists describe this as topological protection, and it's the reason Microsoft calls its approach topological quantum computing. If it works the way Microsoft hopes, the payoff would be substantial. Qubits that are far more resistant to errors by design, potentially requiring dramatically less overhead for error correction than transmon or trapped ion systems need today, which could in turn make it realistic to scale up to much larger, more powerful quantum processors, faster than competing approaches allow. That's the promise behind Majorana-1. Microsoft's own announcement described it as the world's first topological core, built using an entirely new material stack that the company says it designed and fabricated atom by atom. Company representatives said the chip is designed to eventually scale toward roughly 1 million qubits on a single processor, an enormous leap from where quantum computing currently stands, and CEO Satya Nadella described a clear path toward that kind of scale. The underlying research paper, published in the journal Nature, described a useful, commercially relevant quantum machine as achievable in what the authors called years, not decades. Those are big claims. And almost immediately, they ran into serious pushback from parts of the physics community. The core of the dispute isn't about engineering, it's about evidence. Majorana particles have never been definitively, unambiguously observed and confirmed by independent researchers, despite nearly a century of theoretical interest and more than a decade of experimental attempts across multiple labs, including Microsoft's own earlier efforts. Microsoft's claim rests on a specific kind of measurement called single-shot parity readout, essentially a way of checking whether a nanowire device is behaving the way theory predicts it would if it actually contained Majorana modes. Critics argue that this measurement, on its own, isn't sufficient proof that Majorana particles are truly present, let alone that they've been successfully turned into usable qubits. Henry Legg, a physicist at the University of St. Andrews who has published multiple papers disputing Microsoft's results, put it bluntly to reporters, "There is no evidence of even the basic physics of Majoranas in these devices, let alone that you could build a qubit out of them." Sergei Frolov, a physics professor at the University of Pittsburgh, raised a similar concern, noting that the claimed technology rests on basic physics that hasn't actually been established, which he called a significant problem. Even researchers who aren't directly involved in the dispute have urged caution. Bertrand Halperin, an emeritus physics professor at Harvard, not affiliated with either Microsoft's or competing quantum efforts, described the entire field as still being in its early stages. And Harvard physicist and Nobel laureate collaborator on the topic, Halperin has separately said further, "Experiments and better data are necessary before the issue can reasonably be considered settled." Microsoft has continued defending its results and pressing forward regardless. In the months following the initial Majorana 1 announcement, the company introduced a successor chip. And rather than slowing its timeline in response to the criticism, Microsoft actually accelerated its public target for delivering a commercially useful quantum computer, moving the goal to 2029. The objections that critics raised about Majorana 1, particularly concerns about the reliance on a single measurement protocol and the absence of fully independent confirmation of the topological phase itself, have largely carried over to the newer chip as well, since the underlying research on the successor device is still working through the peer review process, rather than having been independently verified yet. To really understand why this dispute is happening now, it helps to know that this isn't the first time Microsoft's topological qubit research has run into serious trouble. The company's search for Majorana particles goes back to research efforts sometimes, associated with Microsoft's Station Q lab founded in 2006, and the road since then hasn't been smooth. In 2018, a different Microsoft-affiliated research team published a paper claiming evidence of Majorana 0 modes in a similar nanowire device, only to retract that paper roughly 2 years later, after other researchers identified flaws in how the original data had been analyzed and presented. That retraction became something of a cautionary tale within the broader quantum physics community, a reminder of just how easy it can be to mistake an ordinary, mundane signal in these devices for the much rarer, much more interesting Majorana signature everyone in the field is actually hoping to find. That history is part of why the current wave of skepticism toward Majorana 1 isn't coming out of nowhere, and why some physicists are being especially careful this time around before accepting Microsoft's newest claims at face value. The stakes of getting it right, and the stakes of getting it wrong and having to walk it back a second time, are both very real for a field that depends heavily on trust in published results. The path from "we detected something consistent with a Majorana mode" to "we built a working error-resistant qubit out of it" is also a lot longer than a single measurement, even a successful one. Beyond confirming the modes exist in the first place, researchers need to demonstrate that they can be reliably manipulated to actually perform computations through a process called braiding, essentially swapping the physical positions of Majorana particles in a controlled way to encode and manipulate quantum information. Multiple distinct operations are needed to build up the kind of controlled braiding sequence that would represent an actual qubit operation, tying and untying these quasi-particle knots in specific patterns. Demonstrating single-shot parity readout, which is what Microsoft's February 2025 paper actually reported, is generally considered an early foundational step in that much longer process, not proof that the full sequence of operations needed for a working qubit has already been achieved. This isn't a case of pure skepticism versus pure hype, though. It's worth understanding that both sides of this dispute are engaging in exactly the process real science is supposed to run on. Microsoft published its results, including the specific data and measurement protocols it used, in a peer-reviewed journal. Outside physicists examined that same data and methodology and raised specific technical objections about whether it actually demonstrates what Microsoft claims. That back and forth, sometimes uncomfortable and very public, is precisely how extraordinary claims are supposed to get tested before the broader scientific community accepts them. Nobody involved is arguing quantum computing itself is fake, or that Microsoft's engineering achievement in fabricating this new materials stack isn't real. The dispute is narrower and more technical than that. Whether the specific evidence presented so far is strong enough to justify the specific claims Microsoft has made about having achieved topological qubits. It's also worth knowing that Microsoft isn't betting everything on this single approach. The company runs two separate quantum computing efforts in parallel. Alongside its in-house topological qubit research, Microsoft's Azure quantum platform has partnered with other quantum hardware companies using entirely different, more established qubit designs through a partnership with Quantinuum, whose machines use trapped ion qubits rather than Microsoft's topological approach. The two companies use Microsoft's own qubit virtualization software to produce 4 highly reliable logical qubits in 2024, an achievement using proven, independently verified qubit technology rather than the contested Majorana approach. In other words, even if the topological qubit program takes longer to pan out than Microsoft's public statements suggest, the company has other, less controversial paths forward in quantum computing, already generating real results. Now let's come back to that other half of the original headline, the idea that any of this might somehow end the AI data center race. This is where the claim really falls apart, because it misunderstands what quantum computers and AI data centers are each actually built to do. Training and running today's large AI models depends on massive parallel arithmetic, multiplying enormous matrices of numbers over and over at incredible scale. That's exactly the kind of workload GPUs, the specialized chips made by companies like NVIDIA and AMD, are extraordinarily good at. Modern AI data centers are built around hundreds of thousands of these GPUs working in tandem, and that architecture has proven remarkably effective at the specific mathematical operations underlying today's machine learning models. Quantum computers are not built for that kind of workload, and they're not particularly good at it. Qubits excel at a narrower, quite different category of problems, mainly ones involving simulating inherently quantum physical systems, like the behavior of molecules and materials at the atomic scale, or certain narrow categories of optimization problems with astronomically large numbers of possible combinations to search through. Training a large language model doesn't look like either of those problems. It's straightforward, if extremely large-scale, matrix multiplication, which classical GPUs already handle with tremendous efficiency. There's currently no serious technical case that quantum computers are about to become better than GPUs at that core task, and most researchers in the field don't expect that to change anytime soon, if ever. What's actually happening, and this is the far more accurate and still genuinely interesting story, is that quantum computing and AI data centers are increasingly being explored as complementary technologies, not competitors. Some researchers are looking at hybrid setups where a quantum processor handles a narrow, specific subtask a classical system struggles with, like finding the ground state energy of a molecule in a materials science problem, and then hands the results off to conventional GPU-based systems to complete the rest of the workload. Companies including IBM have begun experimenting with quantum computers, running physically alongside classical supercomputers in the same facility, and some industry analysts expect quantum processing units to eventually join GPUs and CPUs as one more specialized tool inside AI data centers, handling specific niche tasks like certain optimization or sampling problems, while classical hardware continues to handle the vast majority of actual AI training and inference. That's a meaningfully different picture than quantum chips ending the data center race. It's quantum computers potentially becoming one additional narrow tool inside those same data centers somewhere down the line, assuming the underlying hardware challenges, including the very disputes currently surrounding Microsoft's topological approach, get resolved. Even the most optimistic researchers in this space describe quantum's likely role as a specialized coprocessor for particular bottleneck problems, not a wholesale replacement for the GPU-driven infrastructure currently powering AI. And that's assuming today's most ambitious quantum hardware claims hold up to the kind of independent scrutiny they're currently receiving in the first place. There's one more piece of the puzzle worth including, because it's often what people are actually gesturing at when they imagine quantum computing somehow rescuing AI infrastructure from its current growing pains. Energy. AI data centers consume enormous, rapidly growing amounts of electricity, and that demand has become a genuine strain on power grids in some regions, along with a significant driver of new data center construction. The hope some commentators express is that quantum computers, which can in theory solve certain problems in dramatically fewer computational steps than classical hardware, might eventually offer a way to reduce that energy burden. There's a real, if narrow, kernel of truth here. For the specific kinds of problems, quantum computers are actually suited to deep molecular simulations, Certain optimization tasks, they could in principle require significantly less total energy to solve than throwing enormous classical computing power at the same narrow problem. But that potential efficiency gain applies to a specific, limited slice of computational tasks, not to the broad matrix multiplication workload that defines training and running today's large language models. Quantum computing becoming a genuinely useful energy-saving tool for those specific niche problems is a real, actively researched possibility. Quantum computing solving the energy demands of AI data centers broadly is a much larger, much less supported leap. It's also worth being honest about timelines here, since that's usually where the most sensational claims tend to hide. Microsoft's own public statements have described a commercially useful topological quantum computer as achievable in years, not decades, with a specific target date of 2029 for reaching that milestone. Independent physicists, including several of the same researchers who've directly disputed Microsoft's underlying Majorana claims, have generally described the broader field of quantum computing as still being in its early stages, without offering their own competing firm timeline for when a truly fault-tolerant, large-scale quantum computer of any kind might arrive. That gap between a company's own optimistic public roadmap and the more cautious, uncertain language coming from outside researchers is fairly typical of how emerging technologies get discussed publicly, and it's worth keeping in mind before assuming any specific date is guaranteed to hold. None of this is to say Microsoft's work here isn't worth paying attention to. Building an entirely new material stack, fabricated with the level of atomic precision Microsoft describes, represents a genuine, difficult engineering achievement regardless of how the Majorana dispute ultimately resolves. If the topological approach does eventually pan out as Microsoft hopes, even on a longer timeline than the company's current public statements suggest, it could meaningfully change the trajectory of quantum computing. As a field, potentially making large-scale, genuinely fault-tolerant quantum computers achievable sooner and with less overhead than competing approaches currently require. That would be a real, significant development in its own right. It just isn't the same thing as ending the AI data center race, and it isn't a settled fact yet either. So where does that leave the real story? Microsoft has built something genuinely novel, an entirely new class of quantum hardware based on decades of dedicated research, using physics that, if it works exactly as intended, could offer real advantages in stability and scalability over competing quantum computing approaches. Whether Microsoft has actually achieved that goal is a live, contested scientific question right now, being worked out in peer-reviewed papers and public conference debates, not a settled fact. And regardless of how that specific dispute resolves, quantum computing more broadly is not on a path to replace the GPU-based data centers currently training and running today's AI systems. The two technologies are aimed at different problems, and the most credible vision for their future isn't one replacing the other, but the two eventually working side by side, each handling the part of the job it's actually suited for. That's a more complicated story than a headline promising quantum chips are about to end the AI data center race. It's also a much more honest one, and honestly, a more interesting one too. A company betting on one of the hardest, most contested bets in modern physics, facing real scientific pushback in real time, while quietly hedging with more conventional approaches in parallel, all while the technology it's chasing, even in the best case, was never actually positioned to replace the infrastructure currently running the AI systems. So many headlines assume it's about to make obsolete.